welcome back to another lecture. So in this lecture, we're going to go through molecular orbital theory and also geometries. I'm talking about hybridization. So during the last lecture, I went through how to draw a molecular orbital diagram, and we practiced it for hydrogen molecule, helium ion, and I said like why we don't have helium molecules. So in anytime we're talking about molecular orbital, as it says molecule, and that means the orbital will be distributed over entire of the molecule, not just one specific atom. So in this case, for example, we see there's an electron density, distributed between oxygen and CH3. So it's not specifically sitting on oxygen or say CH3. This area, I'm going to call it CH3. Okay. And also here we see node. Okay. We do have a bunch of nodes between the orbitals. So clearly here we have more than one node. So again, anytime we're talking about molecular orbital, we're not talking about atomic orbital. Is not located on only just one atom. It's distributed over entire of the molecule. Okay. Now we have a ground state and excited state. What's a ground state? Whenever you put the electrons inside the molecular orbital diagram, the lowest electron configuration that you get under normal temperature, we call it the ground state. So now we're going to have some occupied orbital, unoccupied orbital, and for example, the lowest occupied orbital, the highest occupied orbital, we call it HOMO, the highest one, and the lowest unoccupied orbital, we call it LOMO. So let me show them on diagram that we practice for hydrogen molecule. So we practiced this one last time. This is the molecular diagram for H2. We have two hydrogen atoms are reaching each other, two atomic orbital reaching each other, giving us two orbital bonding or sigma SS orbital and sigma star orbital. The lowest, okay, the highest, forgive me again, the highest occupied orbital, we're going to call it the HOMO. So in this case, the HOMO, okay, HOMO is going to be the highest occupied orbital. And for hydrogen, this is going to be the HOMO. The lowest unoccupied orbital, it will be the sigma star, and this one, it will be the LOMO. Okay, so sigma star, it will be the LOMO, and HOMO, it will be sigma SS. Okay, so now I'm going to switch to hybridization. How do we get hybridization of one, for example, one atom, one specific atom, and how, we connect actually atoms to each other by using, for example, atomic orbitals. Okay. And we went through, in Chem 1314, we went through electron configuration. We said we have a process that we take atomic orbital, we mix them, and we get hybrid orbitals. The hybrid orbitals we get, they're gonna give us a chance to technically make a sigma bonds with outer atoms. What I'm talking about, an atom like carbon in methane. Okay, carbon, methane. Carbon, it has electron configuration of 1s2 to 2s2 and 2p2. Last orbital is a p orbital. It has two electrons in it. This is px, py, and the last one is pz. How about the s orbital? S orbital, it has two electrons. Okay, and that's going to be the 2s orbital. Now, if I look to an orbital that are available to make a sigma bond, I have only px and py. And remember this, that the bond angle between x, y, and z, it will be 90 degrees. So if we call this one x, this is y, this is z, and this is y. This one, it will be 90 degree. And same thing here, that's going to be 90 degree because they are perpendicular. So if I use, for example, a px and py and make interaction with carbon, I should get bond angle around 90 degree. So assume you have carbon. This is going to be one p orbital. Call it whatever you want. So call this one. So let's say I call this one py. Where is the pz? Is going to be so px is going to be perpendicular to the py. So I'm going to say this is a plus here, minus. Let's introduce hydrogen. Hydrogen, when it's reaching it, is going to reach the first empty orbital, half occupied orbital. This is the half occupied orbital. We have px, and we have py. So those two are hydrogen. They will come with one electron that is pointing down. And now we managed to get two sigma bonds. So let's show hydrogen. So say hydrogen reached the system from here with one electron pointing down, and the p orbital had one electron pointing up. So I can erase this one. Let's say the p orbital had one electron pointing up. Okay. Now where is the px? Let's put the px here. Okay, we're going to put one electron inside the px, and I'm going to call this one px. Again, hydrogen is going to reach it from this direction. Okay, and it will be pointing down. So I managed to get two interactions. One interaction here, and that's going to be the second interaction. And those two interactions are going to give me sigma. Why? Because it's a head-to-head interaction. So I got two sigma bond. Okay. Now, what's the bond angle between these two sigma bonds? Okay, this is the bond angle between them. The bond angle between X and Y should be 90 degree. Okay, it should be 90 degree because they are perpendicular. And I only accommodated two hydrogens, only two hydrogens. Well, this one, it says we are supposed to have 4 hydrogens. So you need to answer 2 questions. First, how can we connect how can we connect 4 hydrogens to carbon? That's the first question. The second question, the bond angle for CH4, the bond angle for carbon, hydrogen attached to carbon attached to hydrogen is around 109.5 degree. It's bigger than 90. So how can I increase the bond angle to 109 and also have 4 identical CH bonds? Okay. We have something that we call it hybridization. So you start with this. Valence electron, only valence electron. Take the valence electrons. Write the valence electron for carbon. 1s2, 2s2, 2p2. Valence orbitals are 2s and 2p. Valence electrons will be 2 plus 2. We have 4 of them. Okay, so totally we have 4 valence electrons. So I'm going to say 2, forgive me. Okay, I go 2. Where did I get this 2 from? Here. Plus another 2. Where did I get the second 2? That's the second 2. Okay, I have 4 valence electrons. So what I'm going to do with those, I'm going to say I have 2s with 1 electron pointing up. The second one is pointing down. How about the p orbital? P orbital, it has 3 orbitals, px, py, and pz. Okay, inside the p orbitals, we have 2 electrons, and both are pointing up. Okay, we're going to give this system energy. So let's supply some energy. Okay, this is going to be energy is equal to h nu. Okay, so we applied energy to the system. And electron that I'm highlighting, I'm going to send it to the first empty orbital. While I'm sending up, and also I'm going to flip the speed. So we're going to send this electron to higher orbital. Okay, so let's send this electron to higher orbital. Okay, which electron? This electron. And I will get, again, 3 orbitals of p, and s orbital stays it is. But we lost 1 electron, so there's 1 electron pointing down. This is 2s with 1 electron. It used to be 2. Okay, now a p orbital, I got 1, 2, and that's a new one. Okay, look at it. It's pointing up. Used to be pointing down. Okay, this is px, py, and pz. Technically, I have 3 p orbitals. Next, add these 2. Okay, add them. When you add them, you're gonna get like an answer that is somewhere between them. Answer or average of them is going to be somewhere between those 2. So put this way, here on the left side, we're going to say this is showing energy. As we go up, energy increases. Now, if I mix these 2, I get 4 orbitals. 1, 2, 3, 4 orbitals. Okay. 4 orbitals. How did I get those 4 orbitals? I took 1 from S and I paired it with 3 from P. Okay, so I'm going to say SP. SP, SP. How many from S did I use? Just 1 orbital. So I go S1, S1, S1. How many from P did I use? 3 of them. So I go P3, P3, P3 to show that I'm using 3 from P and 1 from S. So I mixed 1 from S and 3 from P. I got 4 orbitals, 4 hybrid orbitals. Okay. And each orbital, it has 25% S character and 75, 3 out of 4 p character, or 75 p character. Totally, I got 4 singly occupied orbitals. So in each orbital, it has 1 electron in it. Okay, so now we have 1 electron in each orbital. Okay, let's show those 4 orbitals on carbon. So now we have carbon with 4 orbitals. 1, 2, 3, and that's the 4th one. Okay, each of this orbital, I'm going to call it hybrid orbital. Okay. Now, the process of mixing S and P, we call it hybridization. So the process of mixing them, we call it hybridization. I mix S and P, I got hybrid orbital, and what's the hybridization for each orbital is S1P3. S1P3. No need to write the 1. Next, carbon is group 4. What does it mean? It means it has a 4 valence electron. Four valence electrons, so no need to show you the charge. Okay, so let's show the valence electrons on carbon. Okay, so I'm going to show the valence electrons on carbon. Okay, you're going to put 1 electron in each orbital. Okay, now what's the bond angle between this hybrid orbital is around 109.5 degrees. So now I got the answer technically why the bond angle is 109. Okay, I answered one question. Next, I need to answer how can I get 4 identical or CH bonds? So I need to have 4 identical CH bonds. Okay, you have 4 identical hybrid orbitals. Hydrogen is going to reach them. Hydrogen is going to reach them from this side. That's hydrogen. And hydrogen is coming with 1 electron that is pointing down. Now you manage to get new interaction. And what's that interaction? We call it sigma. So that's a sigma bond. Okay, so that's the way you get the hybridization for like a compound like CH4 and answer why the bond angle is around around 109. Okay, so let's move on and practice more example. So for CH4, we said we have 25%, 1 out of 4, okay, out of 4, okay, or 25% S character, and 3 out of 4, we have P character, and that's going to be 75% P character, because we are using 3 P orbitals, mixing them with 1 S. And look to the energy of the new orbital, the hybrid. They are somewhere between S and P. They are lower than P because S, it has lower energy than P orbitals. So the average is going to be somewhere between them. Clearly, it's going to be closer to the 2P orbitals. Why? Because you are using 3P orbitals and you are mixing with only 1 S orbital. So it's higher than the midpoint and closer to the P orbitals. Okay. Now, I showed you this in hybridization and what's the bond, why the bond angle is 109. But let's switch to compound like C2H4. Okay. If you're dealing with atom like carbon and you want to figure the hybridization for it, okay, atom like carbon, use this formula, sp3 minus n. Okay, and what's the n? N represents number of pi bonds. Okay, for CH3, the CH4, we had 4 sigma bond. So we had 4 sigma and 0 pi bond. Okay, so how do I get the hybridization for carbon? You will say sp3 minus n, and n, we got it equal to 0. So this is equal to, technically, this is equal to n. So n, we got it equal to 0. So that's going to be sp3 minus 0 still is going to be sp3. Okay, that's one, short formula that always is going to work for carbon. Okay, how about this two? How about this two molecule? You have carbon attached to another carbon. Sigma, 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 sigma. The first bond always going to be sigma, always. Okay. Now, if you have double bond or triple bond, the second and third will be pi bond. So now that's going to be a pi bond. Okay. How do I get the hybridization for it? Okay. For any carbon, you will say sp3 minus n. sp3 minus how many pi bond we have? We have 1 pi bond. 1. So the hybridization, it will be sp3 minus 1. That's going to be sp2. Okay, how about this? We have carbon, hydrogen attached to carbon, and there's a triple bond. Now carbon, and again hydrogen. Okay, what's the hybridization? Okay, pick any element. Okay, let's say that carbon. Okay, what's the hybridization for it? In this case, I have sigma, 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 and these two are pi bonds. So number of pi bonds, I have it equal to 2. So hybridization for carbon, it will be sp3 minus n. That's going to be sp3 minus 2. That's going to be equal to sp. Okay, or s1p1, which is equal to sp. Okay, so that's one easy way actually to find the hybridization for carbon. Next, let's talk about the bond angle. Okay. If you're dealing with, so I'm going to write here, hybridization. Okay. Bond angle and example. Okay. If you're dealing with sp3, okay, and this is one example, perfect tetrahedral. Okay, this one, it will be, the geometry, it will be tetrahedral. The bond angle for hydrogen attached to carbon, attached to another hydrogen. Okay, this sign represents angle. It will be around 109.5. So sp hybridization will give you will give you geometry of tetrahedral, okay, tetrahedral, and the expected bond angle, it will be 109. Okay, what if is sp2? sp2, this is one example for it. B, okay, attached to F, attached to F. Okay. Or let me stick with carbon. Okay. Say you have hydrogen, carbon attached to those. And I can make this one say carbon, double bond here. Okay. Hybridization clearly is sp2. Okay, what's the bond angle? Which bond angle? Okay. If you look at this bond angle, expected bond angle here is around 120. Okay, how about this bond angle? The bond angle here, also expect this one to be around 120. Okay, so the bond angle between hydrogen, carbon, hydrogen, we expect it to be around 120. Bond angle between hydrogen, carbon, carbon, that one also expected to be 120. Okay. Now, what if you change this one to sp1? Okay, sp1 or sp. Okay, an example, you go H attached to carbon, and now triple bond, carbon, H. I'm looking for this bond angle. Okay, what's the bond angle here? The bond angle when the hybridization is sp, it will be 180 degree. Okay. So if I want to summarize them really short version, sp3 has bond angle. Okay, bond angle around, expected bond angle to be 109.5, and the geometry we expect it to be tetrahedral. sp2 bond angle expected to be around 120 degree, and geometry expected to be trigonal planar. Okay, trigonal planar. Okay, I'm talking about this geometry. Okay, it's completely flat. Okay, what's the bond angle between the yellow and red and yellow atom? And the bond angle here is around 120. Okay, system is completely flat. Okay, and how about sp? Expected bond angle is 180. Geometry, we expect the geometry to be linear. The sp3 hybridization always trying to give you tetrahedral geometry. sp2, it will be flat and it will be trigonal planar, and sp always will be linear geometry. Okay, so I'm going to pause here. In the next lecture, I will try to go more in deep in hybridization, and I'm going to show you some method to find the hybridization of any atom in any, like in any technically molecules. And I will see you soon. Thank you very much.